For 3 centuries, if you wanted to measure time, you relied on this sound, the steady, mechanical tick of an escapement wheel. Looking at this animated waveform, you can see the physical sealing of those mechanical watches. The balance wheel and hairspring inside them operate at a very low frequency, typically between 2.5 to 5 oscillations per second, or hertz. Because that frequency is so low, the entire system is fragile. Gravity pulls on the balance wheel, physical shocks disrupt the rhythm, body heat expands the metal hairspring, losing seconds every single day. That margin of error was acceptable for daily life on Earth, but by the 1960s, aerospace engineers were strapping astronauts to rockets. They needed instruments that could keep exact time while enduring massive G-forces and extreme environments. Early attempts to build a better watch, like the Hamilton Electric 500 seen here, fell short. They used a tiny battery, but they still relied on that same fragile, low-frequency balance wheel to keep the beat. Strapping a new power source to an old mechanism didn't fix the core physics problem. To build a watch fit for space exploration, someone had to throw away the balance wheel entirely. In 1952, a Swiss engineer named Max Hetzel, working for the Bulova watch company, did exactly that. He threw out the balance wheel and replaced it with a tuning fork. A tuning fork is an acoustic resonator. When you strike it, it vibrates at a highly stable, specific pitch. Hetzel realized that if he could shrink one down, its stable vibration could act as a nearly perfect metronome. To keep that tiny fork vibrating without physical friction, Hetzel built a hybrid system. He used a newly invented piece of solid-state electronics, the Raytheon CK722 transistor, to act as an electronic switch. This flowchart illustrates how the electronics drive the mechanics. The transistor takes energy from a tiny battery and pulses it through 2 microscopic electromagnetic coils. Inside those coils is about 160 meters of copper wire, drawn so thin it's a fraction of the width of a human hair. Those coils emit a pulsating magnetic field. That field strikes the magnets on the tuning fork, physically pushing it back and forth to create a tight, rapid waveform of 360 hertz. At 360 vibrations per second, the Bulova Accutron moved nearly 150 times faster than a traditional watch. It didn't tick, it hummed. Generating a 360 hertz vibration created a massive engineering puzzle. How do you convert the rapid back-and-forth motion of a tuning fork into the continuous circular rotation needed to turn a watch's hands? This animation shows Hetzel's solution, the Paul and Jewel index. A microscopic ruby jewel sits on a vibrating tuning fork prong. As the fork vibrates forward, the jewel catches a gear tooth, pushing it exactly 1 step. Pulling back to see the whole mechanism, the scale of this micromechanics becomes clear. That index wheel is only 2.4 millimeters wide, but it holds 300 microscopic teeth. The jewel pushes that wheel forward 38 million times a year. Because the tuning fork vibrated so fast and had no delicate balance spring, it was highly resistant to gravity and shocks. Bulova guaranteed the Accutron to be accurate to within 2 seconds a day. That precision under pressure caught the attention of the CIA. When they began flying the A-12 spy plane at Mach 3, cockpit temperatures could exceed 120 degrees Fahrenheit. The Accutron astronaut model was chosen specifically because it could survive the heat. NASA made a similar calculation. While astronauts wore mechanical watches on their wrists, the timing instruments integrated into the Apollo navigation systems and the experiments left on the lunar surface were powered by Bulova's tuning forks. By removing the traditional escapement, Bulova engineered the only timekeeping mechanism robust enough to operate flawlessly in a zero-gravity vacuum or a supersonic cockpit. The Accutron's most famous design actually started out as a sales tool. Bulova created the dial-less Space View model simply as a display piece, so jewelers could show customers the radical green circuitry and copper coils inside. But customers didn't want the standard models. They demanded the display versions. The exposed circuitry quickly became a pop culture icon, worn by celebrities like Elvis Presley. The Space View's inside-out aesthetic spilled over into other disciplines. When architect Richard Rogers was designing the Centre Pompidou in Paris, he looked at the Space View on his wrist and modeled the building's exposed, colorful structural tubes directly after the watch's visible electronics. The Accutron took the hidden mechanics of timekeeping and put them on display, turning raw, functional technology into a celebrated design language. Yet, by proving that battery-powered electronic timekeeping was superior, the Accutron paved the way for its own destruction. In 1969, Seiko introduced the quartz watch. Instead of a metal tuning fork vibrating at 360 Hz, it used a microscopic quartz crystal that oscillated silently at an astounding 32,768 Hz. Quartz watches used solid-state integrated circuits that could be mass-produced cheaply. They were far more accurate than the Accutron and completely eliminated the need for complex, expensive micromechanics like the 300-tooth index wheel. By 1977, Bulova ceased production of the tuning fork watch. But for a brief, critical window during the space race, that humming metal fork served as the essential missing link, bridging 3 centuries of mechanical clockwork with the arrival of modern digital electronics.